Okay, let's see what it's like solving a differential equation in MATLAB. Now, there's some very good differential equation solving tools here, and I'm just going to touch on a couple of them early on like this. First thing we're going to need is an actual differential equation. So I found this one in I don't know, a book somewhere, I think. It's simply dy over dx, or y prime if you prefer, is the square root of x plus y. Now remember, y is y of x. Y is a function. And y is the function that we're going to have to find in order to solve this differential equation. Now, if there's a benefit to the analytical solutions you learned in your differential equations class, if you took one, it's that you'll actually know y. It'll be a closed form function, probably. And you'll actually be able to write down the function that solves that equation. When you're doing numerical solutions, that's not true. Philosophically, basically, what you're doing is you're drawing a picture of the function that solves the differential equation, but you don't know what the actual function is. Now, does that matter? Most of the time, not. Having a really good picture of the solution is just as good as having the solution for engineers and scientists. You know, if you're a mathematician, that won't do. Now, if you look at the differential equation, you'll see that if you knew y and you knew x, you could figure out a slope. So let's just do that. Let's take a range of x's and a range of y's, and I'm going to do something called a quiver plot or a vector plot. It has two different names in MATLAB, and we're going to see a vector field. So let me just run you through the MATLAB commands here. First thing I'm going to need is a list of x's, and I've got all this typed in my command history, so I'm just going to pull this up so you don't have to watch me type all this stuff. So I'm going to let x go from 0 to 10 in steps of 1, which is the default, and I'm just going to say y equals x. So I've got two vectors that are 11 elements long over here. Now, in order to make this plot, I need a grid of x's and a grid of y's, and it turns out there is a function called mesh grid that does that. So when I type in mesh grid, and I'm going to reassign x and y, notice those went from being 1 by 11 to 11 by 11. So these are now matrices. Next thing I'm going to do is I'm just going to calculate the slope at every point, just like the equation says, because remember, dy over dx is the square root of x plus y. Well, if I know x and y, let's just plug those in and see what happens. I'm calling this dy. I guess I could call this dy dx or something like that, but that's the variable I've chosen. So there it is. Now I have a value of the slope at each one of those points. Now, if I could make vector components at all those points, I could draw them out in what's called a quiver plot or vector plot. So let's just do that. I need to know the angles, and that's just the arctangent or inverse tangent of the slope at every point. So notice I've got now a variable called angle, and that's also 11 by 11. So I got a lot of these matrices floating around now. And I need the horizontal value of each vector, the length in the x-axis, I guess, if you want to look at it that way. It's cosine, and the vertical is the sine. Now I have all the pieces. Command in MATLAB is called quiver. Now, this isn't quiver like shaking. This is quiver like a quiver of arrows, I think, because what appears on the plot is arrows. Let me explain what all this stuff is here. So there's x and y. Those are the locations of the base of the arrows. Horizontal and vertical are the length of the arrows. Now I went ahead and divided them by 2 because if I didn't do that, the arrows got kind of long and they got kind of crowded on that plot. So the divide by 2 is just to shorten the arrows. And I'm going to make the arrows blue. I'm going to turn the grid on, hit return, and there it is. Now, got a few problems here. One of them is I don't like the axes, and the other one is that plot isn't square. So I'm going to move this to the side here, and I'm going to say axis square. And you'll notice now the axis is square, so everything's proportional. Better proportion than it was. I'm going to make this as big as I can for you. There we go. That's looking good. Now the other one is that the x and y axes aren't the same, so I'm going to go ahead and hardwire the axis limits in. I'm going to go from negative 11 to 11 in both directions. And so there, that's looking pretty good. So you can see that at every xy point in this field, there is a slope. Right there, the slope is 0. Well, if the square x, and we can actually see there, I've got that data tip visible. X equals 0 and y equals 0. Well, the slope, dy over dx, is the square root of x plus y. Well, that's the square root of 0. That's 0. So at that point right there, the slope is 0. At every other point in the field, the slope is something else. So if I go right there, okay, that's x equals 4, y equals 8. Well, let's see, what's the square root of 12? That's the slope. And you can see there's the components there. So the solution to the differential equation is a curve that follows a path dictated by these arrows. This is a vector field, and as the solution moves through this field, at every grid point, so there, wherever it hits one of these points, it has to have the same slope as those arrows. So the problem now comes, if I'm only going to draw one curve through this field, there's an infinitude of curves that could pass through this field. How do I know which one? I have to know one point on the curve to know which one to pick. Well, in the example that I just showed you, there was an initial condition. Y at x equals 0 is 0. What that means is the curve has to start at x equals 0, y equals 0. So it has to start right there. If I know one point, and I know in this case I know where it starts, this is called an initial condition, and that means this kind of equation is called an initial value problem. But if I know where to start, that starting point dictates the rest of the curve. All right, so what will that look like? Well, like I said, there are many differential equation solvers in MATLAB. The one you're going to use most of the time, I think, is called ODE 4.5. And that 4.5 means something. There's a class of solvers called Runge-Kutta solvers, R-U-N-G-E space K-U-T-T-A. Those are the two people who, well, two of the people who helped develop it. And they have different orders. Explaining how they work is a little beyond the scope of this class, but it's correct enough to think of them as a more sophisticated extension of a finite difference method. There's a lot more to it than that, but that's kind of the starting point. So how do you use one of these things? Let me go ahead and clear the screen here, clear the command window. Now, the RK solver needs to know three things. It needs to know the span in the x direction, the beginning and end points in the x direction. It needs to know an initial condition, and it needs to know what the equation is. So let's start with the range we want to use. And the example I pulled this from used the variable x span to define the range. So let's go from 0 to 10. We need an initial condition, so I'll say y0 equals 0. Again, I'm just pulling these up off the command history. And the last thing I need is to define the differential equation itself. Now you can do this using an anonymous function if you want, and to keep it tidy, I went ahead and defined the anonymous function right inside the command, the ODE command, ODE 4.5. I could have used this anonymous function definition as a separate command if I wanted. Perhaps if I had defined it as f, what's in the blue here, I could have just used f, but it's convenient to put it inside the ODE 4.5 command. So here it is. So all I have to do is hit return, and you'll see right there, xx and xy exist. Now there's more points because the solver thought it needed more points to get an accurate answer, and it's certainly correct. So let's superimpose that solution over this field just to see what it looks like. So first thing I got to do is tell it I'm about to add something to this. So if I issue a plot command, don't erase what I've already got. So I'll say hold on, and say plot, okay, x, y, y. And let's see what that looks like. Well, son of a gun, there it is. Now I'm going to make that line a little wider so you can see it here. Nice bright red. There you go. Deselect it here. So let's take a look at what we've got. There's the starting point at x equals 0, y equals 0, which was given by that initial condition. And although you can't really see it here, right at that point, it is horizontal. It does follow that horizontal arrow. And as it goes up through this vector field, you can see that it's parallel to those arrows. It's following those slopes. If I had given a different starting point, it would have a different path through space. Well, shall we try it? Let's try it. Let's change x span here. Instead of going from 0 to 10, let's go from 1 to 10. That way the initial point will be at x equal 1. And we'll leave y 0 equals 0. And let's go ahead and make another xx and another xy. Now, I'm playing fast and loose with this. That curve exists on this plot right now, and I'm about to redefine xx and xy. As long as I don't erase that curve, I think it'll still be there. So let's go ahead and try this. And I'm going to hit return again. So those don't look like they've changed, xx and xy, but the values have changed. Hold on still applies. So let's go ahead and pull that plot command up. But now we need a different color. It was red. How about, I don't know, should we make it blue? Let's see what this looks like. And there it is. It's kind of hard to see. Let me blow this up again for you. Blue might not have been the best color. What are some other choices? Well, let's stick with blue. We'll just make it big here. There it is, and deselect. So you can see that when I picked a different starting point here, the slope was different. The slope isn't 0 anymore. Slope is 1, really, because it's square root of x plus y. Well, x is 1 and y is 0, so square root of 1 is 1. So instead of having a horizontal slope, it's a diagonal there. And you can see it took a different path up through the vector field. And at all points, it's parallel to the vectors around it. So that's what you're doing when you're solving an initial value problem. So let's just recap to make sure everybody's on board here. If you have a grid of x's and y's, you really can just figure out the slopes everywhere and do this vector plot if you want. Now, in a very simple example like this, it's practical. It's not too hard to do that. For more complicated problems, this is going to be just too computationally intensive. The next big idea is that there are some very good differential equation solvers in MATLAB. If you don't know what else to do for an initial value problem, use ODE 4.5. Next video I'll tell you a little more about the different classifications of differential equations and what solvers apply to those. And the last thing is, once you pick a starting point, what mathematicians call an initial condition, that defines the rest of your path through this vector field. And by just changing where I started, I can get different paths. So hopefully this is a gentle introduction to differential equations. The next video, I'll start talking more about the mechanics of how to solve equations and how all the calculations are done. We're going to start with a finite difference solution, and then we're going to compare that to the results from one of the differential equation solvers from MATLAB. So I hope this helps, and we'll talk to you next time.